Hi, good afternoon, everyone. I'm glad that you made it so far. So apparently, direct style is a thing during this year's Scalar Conference. So if you saw the talk about gears, and you probably did, you might be getting a lot of those during this presentation. But this is expected. So actually, I attended the gears talk as well, and I was like, okay, this was exactly my talk, but well, what should I do? Should I go home or should I just tell it? So let me tell you my story as well. Analogies are good, so let's hope we can all benefit from this. So I'm Jacek. I work at SoftwareMill, where I write Scala and teach Scala. And last year I had a chance to work a bit on the OXEN library, and I want to share my experience. So just a quick recap what OXEN is. The official tagline for OXEN is that it's safe direct style concurrency and resiliency for Scala on the JVM. It's written in Scala 3, it requires Java 21 with all the structured concurrency and stuff. In other words, you can think of OXEN as a developer-friendly wrapper for the structured concurrency stuff. And I've been working specifically on two things in OXEN. First thing were channels that you already heard of. You can think like Go channels or Gears channels for now. And retries. You already heard about retries in Gears as well. So I'm going to show you our take on this. Let's start with a bit of history, because as with a lot of things in our industry, the idea isn't that new, the idea of channels. So there were basically two approaches dating back to the 1970s of how things can interact in concurrent system. The first one you are probably well aware of is the actor pattern or the actor model, which was meant to be an asynchronous way of communication, where messages are sent from one party to another and the parties are named. So you get an actor by its name and then you can send the messages. There are some constraints on how the messages are sent, received, and processed. The other one that also dates back to 1970s is called CSP, which stands for Communicating Sequential Processes. So you have processes that communicate. And the initial idea with CSP was first of all that the communication was blocking or rendezvous. I tried my best with my French here. That basically means that the sender and receiver need to meet to exchange a message. So that's why you think of it as blocking. And eventually it developed to a state where the messages are sent via channels. The slide says modern CSP because in the initial CSP there were no channels, but this idea has evolved a bit, and in kind of modern CSP, how we understand it now, how Go understands it, is that we have channels for the parties to communicate. Perhaps you have noticed the asterisk there. So those are the initial concepts, initial ideas behind those models. But it turns out that you can actually mix and maybe transform the one idea to another. So with the actor model, it's like theoretical asynchronous. But depending on how you use it, you can, for example, say that you want message acknowledgement. So this is a bit higher level abstraction that because you send messages using the actor model, but then you need acknowledgements. But then this is effectively blocking, so the parties need to wait for each other to exchange the message. And you can go the other way around with channels, because the initial idea behind CSP and channels was that the sender and receiver needed to meet. So the channel, it doesn't have any buffering, this communication is blocking. But actually you can think of having a buffered channel, and then the buffered channel allows you for having something like asynchronous communication, because the sender can just put the message in the channel, and then at some point the receiver can receive it, but the sender is not blocked by that time. So what are channel operators? Maybe before explaining what channel operators are, we can just have a quick recap what a channel is. Channel in OXEN, at least, and in general, this is data structure. It's kind of a queue, but it has some more capabilities than a queue. For example, you have the notion of propagating completion or errors through the channel. Yeah, but you can think of it as a queue as a way of exchanging messages. So what are channel operators in the end? Well, if you think of composing a data processing pipeline, like you may have heard of these reactive libraries like RxJava, AkkaStreams, stuff like that. And you have a lot of combinators in those libraries that allow you to express some ways to process your data with some kind of, well, operators. So this is exactly the analogy. So if you're familiar with the actor model, you may have used akka and akka streams, and akka streams has all of those map, flat map, something unordered, and stuff like that methods. And this is exactly what we wanted to try to achieve in OX as well. So so the building block for OX is the structure concurrency, because this is what OX wraps around. But we wanted to go a level up in the abstraction, so how you can combine the channels and process the data. And this is basically thinking of data pipelines and channel operators like the ones you have in akka streams, for example. So what makes a channel operator? Well, if you want to build your own, and I will show how to build your own today. First, you need to start with creating the downstream channel, so the channel you would be sending the data to. Then you need to create something then in OX terms is called a fork to receive from the upstream channel. And fork is a way, well, to fork a computation, so to start a thread of execution that is executed asynchronously. Since we are using Java 21, we are using virtual threads, so this is like a cheap operation to start a thread. And thus the fork that you create starts receiving data from the upstream channel. Then you apply some logic, because the whole idea behind creating an operator is to apply some logic to the data and to process it somehow, and you are sending the data to the downstream channel. The next step is to leverage the additional capabilities of a channel when compared to a queue, for example. And this is about propagating the completion and the errors downstream. So whenever you want to signal that you are done processing or there was an error, you want to signal this downstream. This also relates a bit to our approach to handling errors, because there are different paths you can choose when it comes to how to handle errors. The way we chose in OX was, as you can see here, to propagate the errors. So we are not rethrowing, we are propagating the errors, and eventually it's the downstream that becomes aware of the fact that something went wrong. And finally, since your operator was building created the channel that will handle the data sent downstream, you need to return that channel, and this is what your operator returns. So if you have an operator like the map that we will be implementing in a second, you need to return it, and this is passed to the calling party, and this can be used as the tool to process the data. Okay, so it's time for a short demo. As I mentioned, we'll be implementing the simplest stage you can imagine, or the simplest operator, which is a map. If you look at the signature, well, it takes a source. Originally, it's defined as an extension method on a source, so if you have a source, you can just call map on it. Here, for the sake of simplicity, we will be taking a source explicitly. Then you have the mapping function, which is what a map stage would expect. You return another source, so this is the channel that will be returning is also a source. And then you have this one more thing here using OX, which similarly to what you saw in Gears, it represents the capability of being able to run computations asynchronously. So the using OX, the implicit thing here, or the capability, means that we'll be running inside the scope, and we are able to use the fork construct to start our computations. Okay, so let's go through this one step by step. So first of all, we are creating the channel. So we have a couple of methods in the channel object. For the sake of simplicity, we'll be using the rendezvous one, so the direct one, which is blocking. That means that when you send a message, you need to wait for your receiver to pick it up. You also have a way to create buffer channels, or even something that is like an unlimited channel. So that is a buffer of theoretically like very big capacity. Let's assign it to a value. And now, since we are already in an OX scope, so we have the capability of starting computations in the background. We'll start one. Using the fork construct. And now, within the fork, we'll be applying or implementing the actual logic. So the first thing we need to do is receive data from the upstream channel. Our upstream channel is the source S that is passed here as the parameter. So we are going to say we want to receive safe. Then we are going to pattern match on that to handle the data that might come in. Now, what is the receive save thing? Because there is receive save, there is also receive. Well, if you, like a plain receive. Now, if you think about the source that you are getting data from, it might happen that once you read from the source has already been closed. So there was a signal from the upstream that propagated a completion signal, and the source is already closed. And the various variants of receive tell you what happens when the source was closed. And the save variants, so the receive save, send save, and all the others that we'll be using, they don't throw an exception. So they return a union type, which basically doesn't break your logic by throwing an exception. The unsafe variants, so without the save part in the name, they are throwing an exception if the channel that you are sending to or receiving from happens to be closed. So the first kind of data that we can handle here is the actual data. So if we receive a value of A, what we want to do is we want to use the downstream channel, call send save, which again would like gracefully handle the fact that the channel is possibly closed. Then we are going to apply the function f and f of A, and we're going to send it to the channel. Now, this is the happy path scenario, because if you consider the fact that f is something that is coming from the outside, it can fail, so it would be good to handle this failure. So we're going to wrap this inside the try catch. Here we are catching the non-fatal errors, and with those errors, we are going to signal those to the downstream. And again, as you see, we are using the save variants, which return gracefully even if the channel happens to be closed. So now this was the main path of processing data. But as I mentioned, in the channel you also need to handle the propagation of completion or signals or error signals. So we also need to handle them. Those signals come wrapped in a channel closed object, and you have two variants of that. One is done, so we receive a channel close done. This means that we want to signal completion downstream, so we are basically propagating that. So we are calling done safe on the downstream channel. And quite similarly, when we receive a channel closed error, which contains the error, we also do nothing more than propagating this downstream again. Okay, so that's almost it, but you may notice that here we are only receiving a single value from the upstream, and actually we want to keep receiving values until there is anything, so until the upstream channel is closed. So we need to wrap this entire part here in a loop. So we have a repeat while block in OX. The nice thing about this is that since we are in the direct world, this is actually a while loop under the hood, so it's nothing fancy. There is no like I/O stuff for repeating things. It's just a while loop, plain old while loop, nothing more than that. Of course, we need to modify the code somehow, because this expects a condition to be returned, so the stop condition for the loop. So whenever we are done processing, we want to return false to stop it. So here we're going to return false, here as well. The same happens here. And the question is, what do we do after we send? So how do we know whether we want to finish or not? And here we are using a helper method called isValue on the result of sendSave. SendSave gives you a union type, and the union type it's either unit or a channel closed. So that's an information that the channel was closed actually. And if the channel was closed, we also want to stop. So that's why we are calling isValue, which basically checks which of the variants of the union type was returned. So by calling isValue, we can, based on the send result, we can decide whether to continue or not. So there's now one final step that we need to do, which is returning the channel C that we created here. Okay, so it's time to test it. So now we have a source, but you can see that even now this code doesn't compile. If I call the map method here, I have some built-in functions that I think multiply by 2. I would like to apply the function and print all the results. So for each is another existing operator on the channel. If I try to run it again, well, it still doesn't work. Why doesn't this work? Well, you probably remember that if you look at this signature, for example, we are expecting a capability of being able to fork computations. But we haven't provided this capability. So that's the missing thing here, and that's what the compiler error says as well. So the compiler tells us that we need to run inside a supervised or scoped block. So we are going to use the supervised block here and basically wrap this in a supervised. So that would be it. Okay, now that you can see, actually the f function, apart from mapping, is sleeping for a second, so there is like this nicer effect here. Well, it worked, so far so good. We can also replace this f function with a verbose variant that prints the ID of the thread, and which tells us whether the thread is a virtual one or not. So this is kind of a proof that, first of all, these computations are running in a single virtual thread, so there are no multiple threads started in the background, and they are actually virtual. So we are actually leveraging the capabilities that Java 21 gives us. So this was for the basic variant, how to implement the like probably most basic operator, which is map. So now I want to go a step further and see how we can introduce some more like concurrency here. So what we would like to do now is to implement a map par unordered operator, which does mapping as well. So in the end, it applies a function, but it can start a number of computations in parallel. And then as soon as any computation is done, the result is sent downstream. So it doesn't maintain the order of the computations started in parallel. So the code you see here, this is copy-pasted from the implementation of the map, apart from the to-dos. So we have like the next to-dos that we need to implement here. Other than that, there is nothing new here. It's all that you have seen everything in the map implementation. So the first thing we need to do here is to well, start the computation actually. So because when we receive the value, we want to process it in the background so that it's not blocking processing other values. And here we are going to use a fork again, but this time it's going to be a different fork. So this time, instead of using just fork as we did in the map, we are using fork user. So we have a fork here and fork user here. Before I explain the difference, let me just return true here, because for now we don't want to interrupt the loop when we are done processing a single value, because they can be processed in parallel. So now what's the difference between fork and fork user? So a fork started by fork without anything else is something that we call a daemon fork, which means that, well, it's a fork, it starts a background computation, and it is running within a scope, so the surrounding scope. But the thing is that the surrounding scope is going to can end before all the started forks are completed. So whenever the scope body completes, so if it was in a supervised scope, which it will be in a second, then when the the surrounding scope ends, all the daemon forks might be terminated. So the forks are always guaranteed to be completed, but they may be terminated prematurely, like before they are done doing their work. With fork user, the thing is that the supervising scope is kind of blocked, or because it's waiting for all the user forks it's waiting for them to complete. And this is the behavior that we are expecting here, because we want all the items to be processed before the surrounding scope is done. So the first thing we've done here is actually starting the computation in a fork, so starting another background thread, a virtual one. Now there is a tiny adjustment that we need to do here, because when we receive channel close done from the upstream, it doesn't mean that we want to terminate right away, because there might be forks running in the background that are still processing the data. The upstream channel is done, but we are still processing some data. So we're just commenting this out in order not to signal completion to the downstream. And now we are getting to the point that I was speaking of a second ago. We need to create another scope here that is actually going to wait for all the user forks that we started, so the forks started here, to complete. because we only want to like terminate processing once all the user forks started here are done. And here we are using the construct that you already saw, which is starting a supervised scope here, and we need to return it somewhere here. Yeah. I know that I could be using colons here, but like for some reason this is more readable with the braces. That's my preference. Okay, so now we have this supervised scope that is waiting for all the forks here to be done, and then it completes. So which means that then the execution proceeds here. So the line 34 is where the supervised scope ends. Once this is done, the control flow proceeds, and we are here. And now this is the time when we want to signal completion to the downstream. So actually this is the part where we are going to call done save, because now at this point we know that all the user forks started within supervised are complete, and we are free to signal that we are actually done right now. Now the final part that we need here is controlling the parallelism somehow, because this is already going to work, but it's not going to respect the new parameter that we added here, which is the par thing, and it tells us how many computations we want to start in parallel. So this is the final thing we need to handle. And to handle that, we'll be using one of the good old concurrency primitives called the semaphore, and we're going to initialize the semaphore with the value of par. So the initial the number to which we want to limit our concurrency. And we need to do two things now. Well, first of all, we need to acquire the semaphore, or decrease the value. So we are going to do semaphore acquire here before we receive another value. And then we also need to release the semaphore so that we are giving back the capacity to process data. And this is done once we send the value here. So we are doing semaphore release here. And you might have noticed that actually the is value here and the false here is redundant now because this is running in the fork, so it's really not necessary. It's the true here is the key thing that lets the loop run while the forks are running in the background. So once again, what have we done here? First of all, we started a user fork, so the one that would block the surrounding scope until all the user forks are done to apply our computation. Then we disabled propagating completion immediately once upstream completes, because for in this scenario, this doesn't necessarily mean that we want to complete. We also created the surrounding scope, the supervised one, which makes us wait for all the user forks to complete. After this scope is done, we are signaling completion to the downstream. And finally, we are using a semaphore from Java Concurrent to limit the number of computations running in parallel. So now it looks like we are ready to test this implementation. So let's provide, for example, a parallelism of 3 here. We are using the verbose variant. Okay. So now what you can see here is that that we are actually using different threads for that, and you can also see that the parallelism is not clearly visible. You can play with the parallelism value. The important thing is here is that we are actually using different threads for that. Okay, so this is for the demo. This is for the implementation of that, and this covers the first thing that I wanted to talk about. The other I wanted to talk about are retries, which are also there in Gears, so you'll be able to compare. I also would like to give you some more background, like why retries at all. So if you are performing any operations, there are going to fail at some point. So failures are really inevitable. And you need to have a way to deal with them, but they are also often temporary. So this means that whenever you encounter a failure, it might be worth retrying, actually. And you can have various scenarios for failures, so that might require various delays between the subsequent retries. For example, if you imagine that you have a failed concurrent transaction, it's probably worth retrying immediately because this might have been to some concurrency stuff happening, and you can just retry. If you're getting a timeout, it's probably good to wait because the service might be down and there's really no point trying very often. The main question we are asking ourselves before implementing this is whether we are not reinventing the wheel. So we looked at the landscape of what we have. There is a library that we maintain called retry, but this operates on futures. There is cuts retry, but this works in the monadic world, so it needs to your computations to be wrapped in an effect. There is resilience for S that we also created at some point. It's a wrapper around resilience for J, but it's inactive, unfortunately. So we were wondering whether there is anything for direct style, and it turned out that there is not. So we wanted to create our own. The API that we are aiming at is to have a single retry method with a retry policy that you pass to tell how this is going to behave. And actually, recently, there was a new concept introduced to OXEN called error mode, so the API changed a bit, so we have like a couple of retries, but the retry methods, but the idea is the same. You have the operation defined somehow, and you have the retry policy. So what's a retry policy? It consists of two things. First one is the schedule, so it tells you basically how many times you want to retry, with what delay, so you can define those somehow. And there is also a result policy, which means how do you interpret the results, or interpret the errors, actually, that you might be getting. And there is a new thing that will be there. It's still in the PR state, but it will be there shortly, which is called the result callback. So you can do something with your result, like, I don't know, track metrics, do some logging, anything like that. And this will be a part of the result policy as well. So with schedules, there are two types of schedules, actually. One are finite, the other are infinite. The schedule consists of a delay. In delay, you can choose whether you have no delay, so you try immediately, you can have a constant delay, or you can have the exponential variant with some kind of jitter, which is a way of introducing randomness to some randomness, a tiny one, to the delays between the subsequent retries. So this is the way you are able to define a schedule. So there's a data model for that, basically, for the different variants. Now the result policy. So with the result policy, why is it needed after all? Well, sometimes an operation can return a success, which is not really a success. So probably you have seen APIs like that, which return 200, but actually there is an error code inside, and we want to be able to handle that. So an error is not always an exception. Also, there might be errors where you actually don't want to retry, so you want your policy to be able to express that actually there are errors when we are just failing, not doing any retry. So this is the syntax for retry policies. So you can tell whether a result is actually a success, and you can tell when you actually want to retry. Speaking of the implementation, well, there are two things. One is about infinite schedules, because you need to design it cleverly in order not to get a Stack Overflow or something like that. We needed to choose between a loop or writing a loop ourselves or having the compiler write a loop for us. We opted eventually for tailrec, which makes the compiler write the loop for us, but we write recursive code. And there is the direct style thing, which is kind of philosophical, because first of all, you notice that we have been using the old school concurrency primitive. So with direct style, you are able to use thread sleep, you are able to use semaphores, you are able to use while loops. So this is a nice thing that shows that there is life beyond the monadic composition of programs. For me, this was kind of eye-opening. I started doubting in what I already know, because I've been used to writing things in I/O. And then I went to this direct style, and this actually made me think whether the I/O and the monadic composition isn't really a complication, and maybe this is the way to go. So I'm going to leave you with this question, this food for thought. Here's a couple of links to OXEN itself and to blog posts about this. I will share it in Twitter probably or somewhere else, so that you can take a picture. Yep, and that's it. So thank you for your attention, and if you have any questions, I guess you can catch me later. Yeah.
Now we can try now. If there are any questions, we can try now.